For Units 3 to 6 of Module 3, for Geometric Design of Highways and Railroads, we will be discussing 4 types of sight distances. And for this unit, we are going to start with the stopping sight distance. So, after this video, the learning outcome should be to demonstrate an understanding of the factors affecting the stopping sight distances for highway geometry, and to compute for the stopping sight distances involving different scenarios. So what is a sight distance before we proceed? Sight distance is the length of the road visible to the driver. There are 4 types: stopping sight distance, decision sight distance, intersection sight distance, and passing sight distance. And as I have told you, we will be starting with the stopping sight distance. So let's define it. It is the length of roadway that should be visible ahead of a driver to ensure that the driver will be able to stop if there is an object in his path. So that is self-explanatory. So a stopping sight distance is the required length of the roadway that we should provide in the design of our highways for the driver to be able to stop whenever there is an object that would block its path. So as a review, we have discussed in the previous video about perception reaction time, which is used to determine sight distances, safe approach speeds at intersections, timing of signals at railroad crossings, and traffic signal change intervals. So if you want to have a recall of this concept, you just watch the Unit 2 of, or Unit 3, Unit 1 and 2 of this Module 3. So these are needed in the determination of the sight distances, perception reaction time. So let's define braking distance, because we will need this in the computations later on for stopping sight distance. And we denote it as d sub b. It is the distance covered to reduce speed from an initial speed v sub 0 to a final speed v. So by the time that the driver will be able to apply his brake, so we will now start to determine or measure the braking distance. So we can say that V0 is the speed at the start of brake function. Once the driver was able to step on the brake, we will measure V sub 0. And of course, if you will measure, or if you will step on the brake of this vehicle, then the car will decelerate, or it will reduce its speed to a final speed V, which is 0. You can say that for it to be able to stop, final velocity or final speed, you can say it's final speed, because that we are considering just one direction here, should be equal to 0. Of course, there's a unit, for example, meter per second. Okay, I'll put a parenthesis. So for inclined areas or inclined roads, the braking distance is measured horizontally from the instance when the driver was able to step on the brake to the point wherein the car or the vehicle was able to stop or was able to have a velocity of equal to 0. So if you will notice here, the obstruction or the object is overlapping in the braking distance. So if the car will start stepping on its brake, the object will be bumped because it was overlapping. It has overlapped the braking distance of that vehicle. So the factors that affects the braking distance are, of course, the friction between the tires and the road. Okay, and that is affected by a lot of factors which will be discussed later in this video. The friction force is also affected by the weight of the vehicle. And you have your braking distance. This is B. So for braking distance, we take note of the inclination. We have here the grade, which is the rise over run. So when we say G, that is the grade of the road level. And that is equal to the rise over run. So for this one, this is positive, or this is G, that is the rise. And we consider 1 to be your run para uniform yung notation of G, or uniform yung ratio. This is always 1 and this should be in terms of its grade. Example, if you have here a 3, 4, 5 triangle, to determine the slope in terms of G, or the grade, we can say that that would be, you divide all of these sides by 3, you will transform this into the grade notation. Of course, you're not changing the slope or the grade level. You're just changing the notation of these sides. This will become 1.0. This will become the grade, or 4/3. And you have your grade. Okay? So again, for inclined levels or roadways, the braking distance is taken at the horizontal displacement, but for small grades, the incline will almost be like the horizontal, of course. The larger the value of this angle, the larger the discrepancy between the value of x and the braking distance. Okay, but always remember that the braking distance is measured horizontally. Again, v sub 0 is the start, and v is the final. It should be 0 for stopping sight distance. So we assume that the driver height is equal to 3.5 feet above the road level. That's the standard. And the height of the object is between 2.0 and 3.5 feet. Anything that is below this one is not considered in the consideration. You should always consider that the object or the obstruction, for it to be able to for it to be perceived easily by the driver, should be above 2 feet. As the driver sees the object and recognizes it as danger to him, he reacts. So we are done with the discussion of braking distance. We now move to the reaction distance, or also known as braking reaction distance or brake reaction distance. So what is brake reaction time? Going back here, From the start of the perception of the driver, remember the perception reaction process. At the start of the perception, once the driver was able to see this object, we start with the measurement of your brake reaction distance and your brake reaction time from the start of the perception up to the actual stepping on the brake or the actual function of the brakes. So, the brake reaction time, T sub R, is the interval between the instant that the driver recognizes the existence of an object or hazard ahead and the instant that the brakes are applied. Okay? So the minimum reaction time or minimum brake reaction time is 1.64 seconds. This is according to studies, and this was taken from AASHTO. They are conducting studies to develop, of course, the standards of AASHTO. 0.64 is for alerted drivers plus 1 second for unexpected signal. Thus, we have 1.64 as minimum reaction time. For some drivers, it may take up to 3.5 seconds to respond, of course, as we have mentioned or as we have discussed in the previous modules or part of these modules. We know that different drivers react to different circumstances at different ways. So, for approximately 90% of drivers, including older drivers, a reaction time of 2.5 seconds is considered adequate. So, we say that we consider a brake reaction time when it is not given in the problem the design value of 2.5 seconds. So, if it is not given, always consider 2.5 seconds. That is, of course, based on some studies. So the brake reaction distance, again, or the braking, is the distance measured throughout the duration of the brake reaction time. So the corresponding distance that is covered by the vehicle from the time of perception up to the actual stepping on the brake or the actual functioning of the brakes is the brake reaction distance, or simply the distance measured throughout the duration of the brake reaction time. The brake reaction time has a corresponding brake reaction distance. And of course, we can easily determine that using the principles of dynamics. Braking distance is the distance measured starting from the actual operation of brakes leading to a full stop, just a recall. And we can now define our stopping sight distance simply as the sum of the brake reaction distance and the braking distance. So here, at this point, the mechanical lag, after the mechanical lag, the car brakes start to operate and control build up ensues. So at this point, we measure V sub 0. Of course, for the braking distance. At this area, the braking distance of the car is measured. We have a question here: if does the driver stop in time or not? Okay. So we have here the different velocities. After the braking distance, of course, it will have a velocity equal to 0. And again, SSD or the stopping sight distance is equal to the brake reaction distance and the braking distance. So we have different types of two types of approaches for measuring stopping sight distance. First is the basic approach, which is in terms of friction. So SSD is equal to V sub 0 times TR, or the brake reaction time, plus V sub 0 squared over 2G times F, or the friction, plus or minus G. So G is the grade or rise divided by run. We consider negative G for downhill slopes. So, or if the vehicle is going downhill. Original velocity is v sub 0, brake reaction time, friction coefficient, or this is also called the skid resistance. Grade or rise divided by run. Okay, and we also have the Ashto approach, which is in terms of acceleration. SSD is equal to, they are somewhat similar, it's just that we are changing F into A over G. V sub O TR is the same. A is the deceleration of the vehicle. So if in the problem you were given a deceleration rate, of course, in dynamics, that is considered to be negative. But for this one, since that is defined as deceleration already, that is defined as deceleration, it is already known that that should be negative. So when we use this formula later on, this should be in its absolute value because it is already given, or we already know, we have a common understanding that A here is the deceleration of the vehicle. Because how are you going to stop if you will not decelerate? If you will accelerate, you will not be able to stop. You will not stop the vehicle. Okay? And of course, G is the acceleration due to gravity. For uniformity, we will use G equal to 9.81 meter per second squared for metric units and 32.2 feet per second squared for the English units. Later on, we will have examples for these types of computations. Basically, for the other site distances, we consider the same or similar formula, and we will go over that in the next videos. So we have here stopping site distance on level roadways, meaning we considered G to be equal to 0, or it is in level roads. From AASHTO, or the American Association of State Highways and Transportation Officers, we have the Green Book, or their standard. This is the 2011 edition. I think they already have the 2019 edition, but it's not yet available. I wasn't able to look for it. So let's just use this edition. The AASHTO 2011 Green Book. Okay? American Association of State Highway and Transportation Officials. I'm sorry, that's officials, not officers. Okay, so there you have your brake reaction time and the braking distance on level. You add that, you will have the stopping site distance. You have you calculated from the calculations considering different design speeds. So take note that for this one, we considered our brake reaction time to be equal to 2.5 seconds, the 98th percentile, and the deceleration rate is 3.4 meter per second squared. Later we will be discussing this portion. Where did they get this deceleration rate for the design speed? And of course, the calculated should have some allowances. So for that one, they added some distances, and they arrived with the distance or design stopping site distances. Of course, the design should always be greater than the calculated to give some factors of safety or allowances. This is the metric in metric units, and this would be in the US customary or the English in English units. MPH here is in miles per hour. This is kilometers per hour for the metric or kph. Okay. So from AASHTO, this is for the similar to what I have shown you a while ago. These values or factors here are just conversion factors, because if you notice, the design speed here, or the starting v sub 0 in our notation, is equal to kph. So for it to be in meters per second, they introduced this factor 0.039 as the what do you call this, conversion factor. Okay, you already know that. And you have your SSD. Again, this is the factors before the variables are just conversion factors. Don't worry about that. You can just memorize the one that I've showed you a while. And let's have some examples. So we have a problem. Compute the total stopping site distance. This should be total stopping site distance. Sorry for that. That the car moves during an emergency stop based on the following data. So the initial velocity of the car is 60 kph, or this should be v sub 0. The final velocity when it stops, of course, should be 0 kph, or kilometers per hour. Coefficient of friction between tires and pavement is 0.15, and the slope of the roadway is 2.2%. Downhill, perception reaction time is 0.75 seconds. So we have our formula. You are looking for the total stopping site distance, and we know that SSD is equal to the brake reaction distance, VOTR, plus, take note that we are given the friction, so we will use the formula in terms of friction. That should be V sub 0 squared times 2g times friction coefficient plus or minus the grade or the slope. Okay, and since that is downhill, we will use negative slope. So let's just remove this one, or okay, let's just incorporate it here. So the solution for this one should be SSD VOTR plus VO squared over 2g times F plus or minus g. But then, if you will notice, you have your initial velocity in terms of kph, or kilometers per hour. And for us to have our SSD in meters, let's convert this one into meters per second. So the initial velocity, 60 kilometers per hour, so we have here 1000 meters is equal to 1 kilometer, and 1 hour has 3600 seconds. We can cancel this, and this one we will have meters per second. We will have 60 times 1000 over 3600, and that would be 50 over 3, or 16.667 meters per second. So we are now ready to find the total stopping site distance. That would be equal to 16.667. Your perception reaction time is 0.75 seconds. Let me show the cancellation of the units. 0.75 seconds plus, of course, your VO squared, or this would be 16.667. This is squared. If you will square the unit, that would be meters squared per second squared divided by 2 times g. Again, for uniformity, we will use 9.81 meter per second squared, because we are using the metric system. This is multiplied by the coefficient of friction, or 0.15, and that is downhill, so this will be negative 0.02 or 2%. And we now have your SSD, or stopping sight distance total. This would be 16.667 times 0.75. Again, if your perception reaction time is not given, you should use 2.5 seconds. But for this one, the driver is alert. It was given to be 0.75 seconds. Again, plus 16.667 squared divided by 2 times 9.81 times 0.15 minus 0.02. And we have here your total stopping sight distance to be equal to 121.41 in meters. Okay, what if the driver is moving downhill, or uphill rather? So if that is uphill, your G, this one should be positive. So we will have SSD equal to, let me use my calculator, that would be positive. So that should be equal to 95.79 meters. So if uphill, if the driver is going uphill, then it will have a shorter stopping sight distance that is required. Okay, because the weight, of course, using the principles of your dynamics, it's easier to stop. It's easier to decelerate when you are going up. It's harder to do that if you are going downhill, because your weight is contributing to your acceleration. Okay, another problem. We have here, in a braking test, a vehicle traveling at a speed of 30 kph was stopped by applying brakes fully, and the skid marks were 5.7 meters in length. That will mean the average skid resistance of the level pavement surface. So if that is level pavement, we have a grade equal to 0. We have initial speed equal to 30 kph, or kilometers per hour. If this is in meters per second, this will be equal to 8.333 meters per second. And the skid marks were 5.7 meters in length. So skid is also a synonym of friction. So we can say that 5.7 meters is equal to the braking distance. So instead of using the formula for the SSD, if SSD is equal to VOTR plus VO squared over 2G times F plus or minus G. This is the braking reaction distance, and this portion here is the braking distance. So this will be equal to 0 because that is not considered. Or let's just say that the braking distance is equal to V sub 0 squared over 2G times F plus minus G. That is, of course, if you are going to use friction. But if you're using the Ashton method, your F here should be equal to A over G. or VO squared over 2G times deceleration over gravitational force or gravitational acceleration. We have G here. So let's compute for the braking distance, and this is equal to that is equal to 5.7 meters. Because if you apply the brake in this scenario, there will be skid marks or the marks of the tire in the road. This will be very visible if the road that is uh, being utilized in this braking test is a concrete road. Okay, those are the marks that the tires are making with your road, skid marks. So 5.7 is equal to, using this formula, VO squared or 8.333 squared divided by 2 times 9.81 multiplied by F. We are looking for the average skid resistance, the coefficient in this case, and we don't have the grade because that is on a level surface. So let's just say that that should be plus 0. So 0. So F here is now equal to, cross multiplying, we have 8.333 squared. 2 times 9.81 is 19.62 times 5.7, and we now have your skid resistance, the average skid resistance. This is equal to 0.62. Okay, so good. Another problem we have here. A vehicle traveling at 40 kph was stopped within 1.8 seconds after application of brakes. Determine the average skid resistance. Okay, similar to the previous problem, we have a vehicle initial speed is 40 kph, or meters per second. This should be 40 times 1000 over 3600 from our previous conversion. This would be 111.111 meters per second, and it was stopped within 1 seconds after application of brakes. So we have here the time of brake application. Do not be confused. This is the time of the brake application, which means this was the time when we measured the braking distance, not the braking reaction distance. Time of brake application is 1.80 seconds, and we are still determining the value of F. Okay, so our braking distance is equal to I think we call this one d sub b, and this is equal to v sub 0 squared over 2g times f plus or minus g. We don't have any data for g, so let's assume that this is equal to 0, and we are still looking for the value of f. But we have a problem. We don't know the value of the braking distance. What we know is that it was stopped within 1.80 seconds with an initial velocity of 40 kph. And we know that if you're going to stop a vehicle, the final velocity of that one should be equal to 0 meters per second. And from these values, we will be able to look for the value of the acceleration. Okay, so for the value of the deceleration, from our dynamics, this is equal to the final velocity minus the initial velocity divided by the time interval of between these two velocities. So acceleration is equal to 0 minus 11.111 meters per second. This will be 1.80 seconds. And we have the deceleration rate equal to negative 11.111 over 1.8. This is equal to negative 6.173 meters per second squared. And again, we still don't have the value of the braking distance. From your kinematics, we have a formula: final velocity squared is equal to the initial velocity squared plus 2 times the acceleration or deceleration multiplied by the distance s minus s sub 0. But we can also denote this as the change in the distance. We can use this for us to be able to determine the braking distance. We know the final velocity, the initial velocity, and the acceleration. And we can have this delta s. So we can say v squared is equal to v sub o squared plus 2 times a times d sub b. So d sub b in this case is equal to the initial velocity 0 squared, or the final velocity. Transpose this to the other side, this will become negative v0 squared, or 11.111 quantity squared. Cross multiplying to a, we will have 2 times negative 6.173. And this is equal to, using my calculator, we have here 11.111 squared multiplied by negative 1 divided by 2 times negative 6.173, and this should be equal to 9.9995 meters. Let's say this is 10 meters. And we now have your braking distance. So from this formula, braking distance 10 meters is equal to v sub o is 11.111 squared over 2 times 9.81 multiplied by the value of f plus 0, because that is in a level ground. And manipulating the equation, we will have the value of f. You can already manipulate this equation. I will not be showing it So this is equal to 0.629 or 0.63. Okay, so as long as you know the concept of the stopping sight distance, you can compute for these problems. Now we move for the criteria for measurement. Let's just take a short discussion for the design values that was used in the development of this form of the design values for acceleration and for the value of the brake reaction time. So from Ashto, on the Green Book 2011 edition, it is in chapter 3 of page 15 of chapter 3. For all sight distance calculations for passenger vehicles, the height of the driver's eye is considered to be 1.08 meters or 3.5 feet. Here, the height of the driver, 3.5 feet above the road surface. This value is based on a study. So that is based on a study that found the average vehicle heights have increased to 1.3 meters, with a comparable decrease in average eye heights to 1.08. So because of various factors that appear to place practical limits on further decreases in passenger car heights and the relatively small increases in the lengths of vertical curves that would result from further changes that do occur, 1.08 or 3.5 feet is considered to be the appropriate height for driver's eye for measuring both stopping and passing sight distances. For large trucks, the driver's eye height ranges from 1.8 to 2.4. Of course, that should be higher because that is a truck. The recommended value for the truck driver eye height for design is 2.33 meters or 7.6 feet above the road surface. So, from Ashto, the height of the driver's eye above the road surface should be 3.5 feet. That is the design value. And the height of the object that was considered in the analysis is 2 feet. Again, from Ashto, this time in page 16 of chapter 3. For stopping sight distance and decision sight distance calculations, the height of the object is considered to be 0.6 meters or 2 feet above the road surface. For passing sight distance calculations, the height of the object is considered to be 1.08 meters above the road surface. So, just this is the summary of that one. But then, I just want to share that is based on various studies made by in partnership with Ashto. The value of h as per Ashto is based on the rationalization of the size of the object that may be encountered. Okay. The impact on construction cost, a value lesser than 0.6 meters for the height of the passenger car tail heights may increase construction cost substantially. Okay, so 0.6 here is the height of the object here. And that is also the height of passenger car tail heights. Drivers' ability to perceive and react. At high speeds, drivers are limited in their ability to detect small objects. Of course, we have discussed that in the previous modules. Design value should satisfy requirements of nearly all drivers under most operating conditions. And the required time is generally higher under normal conditions than under alerted conditions. Of course, if under normal conditions, you will not be that much of an alert condition. So it will require a higher amount of time for you to be able to perceive that specific danger for you to be able to decide if that is really an obstruction, if that is a danger. And if you're in alerted condition, of course, it should have a smaller time. A time of 2.5 seconds exceeds the 90th percentile of reaction time for all drivers, as I have mentioned a while ago. For extremely complex conditions, 2.5 seconds may not be adequate. Okay? So what are the factors influencing sight distance? These are the speed of the vehicle. Of course, the speed of the vehicle is directly proportional to the required SSD. This means that the higher the speed of the vehicle, there is a higher amount of required SSD that should be provided. This is very visible, or it is demonstrated in the tables that I have showed you a while ago. I think that was table 3.1 or 3-1, describing the or showing different required stopping sight distances or design values for different design velocities or speeds. It is also affected by the efficiency of brakes. 100% efficiency is not desired. The wheels are fully locked, so there is no rotation, skidding, and once vehicle skids, there will be no control of vehicle. So the efficiency of brakes during these conditions or in the design is not considered to be 100%, because in that case, if the speed of the brake is 100% efficient, when you step on the brake, it will automatically be functional. It will lock the wheels, and in that case, since there is momentum in the vehicles, it will not the brake will not be sufficient for it to make the vehicle in a full stop. And the brake in that case, or the wheels are not moving, if the wheels are not moving because the brakes are 100% efficient, the skid will, or the vehicle will continue to move until it will be in full stop, and in that case, skidding occurs. Okay, so I think you already know this from the principles of your dynamics. So I'm just giving you an idea or a recall for this concept. Frictional resistance between the road and tires. The speed of vehicle is indirectly proportional to friction between road and tires. This means that the higher the speed of the vehicle, the lower the friction between the road and tires is. That is why during rainy seasons, it is always advised that we lower our speed when you are driving, because in that case if you are going to drive for example at 20 kph during the rainy season and during a relatively good weather, during the rainy season, even if you are traveling at the same distance or at the same velocity, you will experience a lesser friction during the rainy season, even if you are traveling at the same speed. That is because it is affected by the rain affects the friction between the road and the tires. So for safety purposes, it is always advised to slow down when it is raining. We always see the sign that says the road is slippery when wet. It is also affected by the type of and the condition of the pavements. So here, again, as I have mentioned, the condition of the pavement, if that is wet or dry, affects the friction. And of course, your type, if that is bituminous, macadam, earthen, and concrete. And it is also affected by the tire's type and condition, that is worn out, flat, versus tires with new treads. Of course, a new tire with new treads will have a more efficient or a greater friction. friction coefficient as compared with those who are already worn out or flat. Brake efficiency is considered to be 0.35 to 0.40 depending on the speed. Of course, if the speed is higher, then the efficiency will be lower. Acceleration and deceleration. For the design value, I have mentioned a while ago that we consider a value of 3.4 meters per second squared or 11.2 feet per second squared. So what is the basis for that one? From Ashto Green Book 2011, Chapter 3, page 3, studies documented in the literature show that most drivers decelerate at a rate greater than 4.5 meters per second squared when confronted with the need to stop for an unexpected object in the roadway. Approximately 90% of all drivers decelerate at rates greater than 3.4 meters per second squared. Such decelerations are within the driver's capability to stay within his or her lane rather, and maintain steering control during the braking maneuver of wet surfaces. Therefore, 3.4 meters per second squared, a comfortable deceleration for most drivers, is recommended as the deceleration threshold for determining stopping sight distance. Again, we are using the 98th percentile from the studies that was made by Ashto. Implicit in the choice of this deceleration threshold is the assessment that most vehicle braking systems and the tire pavement friction levels of most roadways can provide a deceleration rate of at least 3.4 meters per second squared. The friction available on most wet pavement surfaces and the capabilities of most vehicle braking systems can provide braking friction that exceeds this deceleration rate. Okay, so that is from Ashto. Okay, that is written in this portion. The deceleration rate of 3.4 meters per second squared is considered to determine these design values for the stopping sight distance. And of course, again, I am reiterating this one, the brake reaction distance predicated on a time of 2.5 seconds. So if it's not given, you should use those values. From Ashto Green Book 2011, page 3-5 and page 3-6, it is stated that the stopping sight distances needed on upgrades are shorter than on level roadways, and those on downgrades are longer. I think I have already mentioned about this a while ago, and we are just reading this from Ashto. Okay, that is self-explanatory. We have also demonstrated this using our first example in the computation. And we have the stopping sight distances for various grades shown in table 3-2. This adjusted sight distance values are computed for weight pavement conditions using the same design speeds and brake reaction times used for level roadways in table 3-1. On nearly all road streets and streets, the grade is traversed by traffic in both directions of travel, but the sight distance at any point on the highway generally is different in each direction, particularly on straight roads in rolling terrain. Generally, the sight distance available on downgrades is larger than on upgrades, automatically providing the appropriate corrections for grade. This may explain why some designers do not adjust stopping sight distance because of grade. Exceptions are one-way roadways or streets, as on divided highways with independent profiles for these separate roadways. Adjustments for grade may be needed. Again, this is for the braking distance on considering the grade. I have already given you this formula a while ago. If you will notice 2.254 here and 30 is not the same with the one I give you. It's just because of some conversions for the value of velocity. Because again, in this formula, the design speed or V is in kph. Here are some stopping site distances for different values of grades, downgrades, and upgrades. You will notice the values in the upgrades or in the downgrades are greater in the upgrades even if they have the same slope. Okay, this is 20, this is 19. You may try to use the formula to determine this one. Of course, they did some adjustments from based on the computed values rather. Variation for trucks. A while ago we have touched about this one. For trucks, we consider a different conditions. From ASHTO again, the recommended stopping site distances are based on passenger car operation and do not explicitly consider design for truck operation. So the values or the design values, the value of 2.5 seconds for braking reaction time and the acceleration of 3.4 meters per second squared for the deceleration rate is considered for passenger cars and it is not considered for truck operation. Of course, for trucks, it will have a greater value. Trucks, especially the larger and heavier units, need larger or longer stopping distances for a given speed than passenger vehicles. However, there is one factor that tends to balance the additional braking lengths for trucks with those for passenger cars. And that is the truck driver can see substantially farther beyond vertical sight obstruction because of higher position of the seat in the vehicle. Separate stopping sight distance for trucks and passenger cars therefore are not generally used in highway design. So although the other factors in trucks will yield to higher or longer values for stopping sight distances or stopping distances in general, it is balanced by the fact that the eye level of the truck drivers are relatively higher as compared with those in passenger cars. So they can see more farther. They can see farther. So generally, we still use the values that we have for passenger cars. There is one situation in which the goal should be to provide stopping sight distances greater than the design values in Table 3-1, where horizontal sight restrictions occurred on downgrades, particularly at the ends of long downgrades, where truck speeds closely approach or exceed those of passenger cars. The greater height of eye of the truck driver is of little value. So if the truck is going downwards or downhill, the acceleration or the deceleration is somewhat hard because it is affected by the weight of the truck, of course, and many other factors. So in that case, you should consider that if you are going to design for downgrades with very high values. Although the average truck driver tends to be more experienced than the average passenger car driver and quicker to recognize potential risks, it is desirable under such conditions to provide stopping sight distance that exceeds the values in tables 3-1 or 3-2. Okay, so to give some factors of safety, you can consider the calculated rather than depending on the values in tables 3-1 and 3-2. As a review, stopping sight distance is the sum of two distances. The first one is the distance traversed by the vehicle from the instant the driver sights an object necessitating a stop to the instant the brakes are applied, or that is referred to as the brake reaction distance. And the second component of the stopping sight distance is the distance needed to stop the vehicle from the instant brake application begins, or what we call as the braking distance. Okay? So if you have questions, don't hesitate to post it in the discussions of our canvas, or if you have a personal concern, you can email me using this email. And here are some of my resources. I'll see you on the next video for our unit 4.